to class. Okay, so we're going to talk about an application of Faraday's law. So what I drew here, say we have two permanent magnets. We have like a north pole and a south pole. And we place a coil in between the poles of the magnets. So the coil could just be like a wire in a loop. Ideally, we'd have several loops of wire. But, the principle applies in any case. So I oriented it, well, I guess this could be an example of a coil. Usually we'd want something smaller though, just because for calculation purposes anyways, we'd like to have like a uniform magnetic field. But I'll use this as our coil. So we've got a north pole of a magnet here and a south pole here. And I oriented it so the normal vector is pointing this way. And so what happens if we rotate this coil? Like right now, let's look at the flux through this coil. So I'm going to say that the flux is NBA. Okay, so N is the number of loops in the coil, B is this magnetic field, and A is the area of like a single loop. So if this is our coil, A would be this cross-section area. Just the loop, not this cardboard at the end. So, that'd be the flux through this coil. And there's also, let's put this cosine theta, where theta is the angle between the magnetic field and the normal vector. Now I initially left this off because the way I drew it, they're parallel to each other. And if theta is 0, cosine of 0 is 1, and so the flux would be NBA. Now let's say we rotate this coil. So it happens, everything else is the same, but this angle is changing. Like if we rotate it through a quarter turn, the flux goes to 0. And so obviously there's a changing flux going on here, which is going to create an EMF by Faraday's law and drive a current. So let's kind of look at what the EMF would look like. So let's say we take this coil and we rotate it with an angular frequency omega. And so in general, let's say that theta is omega t. So after, omega is the angular frequency, that can be used to define how long it takes to complete one rotation. And so if we go through 2 pi radians, one complete rotation, we do, then the time it would take would be the period, and then we'd just be back to 1. So, if omega times t is 2 pi, we completed one rotation. And, cosine of 2 pi is back to 0. We're back to where we started. We completed one rotation. So this would be the flux as a function of time. Now, to get the EMF, I'm going to just have to write down the answer. So note that NBA, these are all constants. The only thing that's changing is time. Omega is a constant as well. The problem is we have a constantly changing flux, and the time dependence is a little complicated here. Now, in a calculus-based class, what we do is replace delta theta over delta t with d theta over dt. Then you'll immediately see what happens when we take when we do that. That's called taking a derivative, if you haven't taken calculus. But the EMF, remember at delta, so we can take all the constants out. And then looking at how this cosine omega t changes with time, I'm just going to write down the answer. We have omega times sine omega t. Now there's a minus sign in front. Yeah, I guess so. I don't want to put the minus sign there. But yeah, I guess I probably should if I'm doing it this way. Okay. So this is what the EMF would look like as a function of time. Here, I'm going to call this epsilon m for maximum value. Because a sine function has a maximum value of 1. It's never going to be more than that. So when sine is 1, or negative 1 in this case, the EMF will be at a maximum. And we can plot this EMF as a function of time. So we have the EMF in volts, time in seconds, and it's described by a sine function. And so this is driving a current, and the current is also going to be described by a sine function as well. And so this is called an alternating current. If we plot the current as a function of time, I was going to say it's going to look the same. Now, it's going to be described by a sine function, but it's not always going to be what we call in phase with the EMF, but sometimes it can be. Let's just say, typically if we just have a simple circuit with only resistance involved, then we can say that these two are going to be in phase with each other. But in any event, it's going to be described by a sine function. And so if we compare this with the current we get from a battery, so for a battery, we just get a steady current. It's a constant. Like if you just have a circuit with a battery and a resistor, you just have a certain current in the circuit, and it remains constant. Now, I guess over a long period of time, the battery can decay and the current will start decaying as well. But as long as the EMF is constant, the current will be as well. So this is what we get from a battery. This is what we get from spinning a coil in a magnetic field. And, very different behavior. So we give them names. We call this a direct current. This is an alternating current. Okay. Now, how often does this come up that we spin a coil in a magnetic field? Is this really important? This is where we get almost all of our energy. Most of it comes from spinning a coil in a magnetic field. That generates an EMF as described by Faraday's law. So, this is a great way to produce energy. For one thing, we can turn mechanical energy into electric energy. So remember, like an electric motor, we can turn electrical energy into rotational mechanical energy. This is the exact opposite. We're taking mechanical energy and turning that into electrical energy, which could be carried by current. So the reason, no matter what type of energy you use, it's probably doing this. Unless you have solar power. Solar power is more of a direct current. But most of the power we generate, like if you just plug something in the outlet, your outlet's connected to a power grid, and that power was probably generated by this. So like if you have an old-fashioned coal plant, all you do is you're burning coal or oil, or you burn something and generate steam. And that steam can go through a turbine, which causes the turbine to rotate, and that rotates this coil in a magnetic field and generates an alternating current. Nuclear energy works the same way. With nuclear, though, they just use the heat from this radioactive decay to heat up the steam and then run it through a turbine. Like wind power. See those windmills, those huge things? The wind causes the the blades to turn. That generates electricity. Hydroelectric, you have a dam. You can open up a gate and let water flow. The water flows through a turbine, generates electricity. So almost everything we do, almost all the energy we use is generated by Faraday's law. Basically, a coil rotating in a magnetic field. Okay, now most devices, though, tend to use direct current. And so it's great. We generate energy, electrical energy this way most of the time. Now, it is possible to convert between the two. You can turn a direct current into an alternating current, or an alternating current into a direct current. But this is how it's naturally produced. And, going way back to the days of Edison, he was one of the pioneers in electricity. And Edison and this other guy, I think it was Westinghouse, they had a big dispute over which of these was better, alternating current or direct current. And Edison favored direct current. The other guy, I think his name was Westinghouse, was in favor of alternating current. This is one of those rare cases where Edison was completely wrong. Alternating current has some property that's extremely useful, which is why it's primarily used. Even though most of our devices use direct current, when it comes to transmitting power, we usually use alternating current. And there's a huge advantage to alternating current that we're going to get to in a later topic. So just keep that in mind. There's a reason that we use alternating current, even though most of the devices we use require direct current. Okay, but I want to talk a little bit about alternating currents. So I'm going to erase this. I erased it, but the EMF, we can get rid of that minus sign. In general, the EMF is given by some maximum value times sine omega t. We have standards in the production and transport of electrical energy. And so, like in America, this omega is fixed. Like the rate that we rotate this coil, I think the actual frequency is 50 hertz or 60 hertz. Maybe there's some leeway. And also we have standards for this, like the actual value of current that we're using, or the EMF that we're using. You might have heard, like in America, we use 120 volts of current. Where in Europe, they use 220. So yeah, those are just different standards that are in effect. And I kind of looked into why we have different standards. And I think the reason is that they kind of made sense at the time for the different regions. Like Europe was much more developed in the 1800s than America. So they had a lot of, things, like most people lived close to each other. And so for them, transmitting things at higher voltage made sense, where in America things were spread out a lot more. So I think ultimately that's why we have different standards. I guess in a way we're fortunate to have standards at all. Some countries don't even have a universal standard. So it's like you can be in some countries and some outlets, like you go to one house and it's 120 volts, go to the next neighborhood over, plug something in, and you fry your device because it's 200 and some volts. So yeah, at least we do have standards for a given area. Now you probably have some high voltage outlets in your house that are at like 200 and some volts as well. They put those in some rooms where like heavy appliances, like sometimes washing machines or refrigerators require higher voltage. But typically, a normal outlet is 120 volts. But what does that mean? Like in America, we have a standard 120 volts. What does that actually mean? Because here, the voltage varies. So, it's not just like a constant 120. I think what that 120 volts is It's kind of like an average. But we have to be a little bit careful when we define the average of a function. Like if we look at a sine function, let's say we look, and again, this is oscillating hundreds of times a second. So even if you look at like a 10-second time interval, there's hundreds or, maybe 1,000 oscillations in that time period. A few thousand probably. And so, in our short time scale, if we take an average value, we're going to get 0. And the reason why, let's just look at one cycle. So we started here, ended here. Now these sine functions are, circular. They're very symmetric. Circular, if you look at a unit circle, if you go around, if you take a dot and go around, the y-coordinate is the sine. If you have a unit circle with a radius of 1, this y-coordinate would be the sine. And so like each of these quadrants is perfectly symmetrical. And so basically this bubble here that's negative is exactly equal to this one that is positive. So when you take the average value of these two, I didn't complete this cycle, did I? Oh yeah. Oh, okay, that's actually a complete cycle. But anyways, yeah, like this bubble and this bubble, they completely cancel each other out. And so the average value of a sine function is 0. That's not very useful though. So what we want to do is define a more meaningful average. All right, we talked about this before. It's called the root mean square average. So again, what we do is, just like we talked about the velocity in a gas. We talked about the average velocity, where a molecule is just as likely to be going, say, in the positive x direction as a negative x, or like in any direction, they're equally likely to be going. And so the average value is going to be 0 over a large collection of particles, like gas molecules. And so we defined an average where we squared everything, and then took the average, and then took the square root. That's what this root means square. So we got to start at the end. So if we square this EMF, everything's going to be positive, and then we can take the average, but then we'll have an average in, like volts squared, where we want to get back to volts, so we take the square root. So this RMS average, and if we take the average, we can use this notation. Let's say that means we're taking the average. This is a constant. We can take that out. So I want the average value of sine squared. Now, I think I went over this before, where I kind of showed in a non-rigorous way that this average is, the average of sine squared is 1/2. And the way I did that is noting that the average of sine squared is equal to the average value of cosine squared. Because sine and cosine are literally the exact same function, the exact same shape. They're just shifted. And so if you look over one cycle, the average of sine squared is equal to the average value of cosine squared. So, yeah, I guess we'll just do that again. So the average value of sine squared, let's just do, in general, sine squared x. That's obviously equal to, and use the word obviously when you're not doing something in a mathematically rigorous way, but we can say that's equal to 1/2 sine squared plus sine squared. So yeah, if you just add these up, you get 2 sine squared times 1/2 sine squared. Okay, and then we can replace one of these sines with cosine because they're exact same function. And now sine squared plus cosine squared is 1. And so the average value of sine squared is 1/2. And then when we take the square root, we get 1 over root 2. So let me just write down this result. So the RMS average is equal to the peak value divided by the square root of 2. So, yeah, if you hear 120 volts as our standard in America, that's the RMS value. So the peak value would be the square root of 2 times the average. So that turns around to be around 170 volt peak average. So you can, yeah, it varies from 170 volts to 0, minus 70, but the average is around 120 volts. Now, current is kind of the same thing. If we just have Ohm's law, so if we look at the current as a function of time, current is the voltage over the resistance. So, yeah, we're going to get the same deal as before. It's going to be described by, let's just plug this in. We have actually, I'm going to do it like this. Okay. And so this we'll call this the peak current. The peak voltage divided by the resistance. So the current as a function of time is going to be, peak current times sine omega t. And the RMS average is going to be the peak value divided by square root of 2. So just like the voltage and the current, the peak values and the RMS values are related by the square root of 2. So I'm going to write these down over here. All right, so the peak EMF, or let's say the average RMS, or the average EMF is the peak value divided by the square root of 2, and the RMS average is peak current divided by square root of 2. Let me write down the equations for these as well. So we can say that the EMF as a function of time and the current as a function of time are equal to the average, or the peak values, plus, multiplied by this sine function. Now, power is current times voltage. So let's look at power as a function of time. So just current times voltage. So let's plug these in. We have peak current times peak voltage. And they're both described by this sine function. So we have times sine squared omega t. So if we look at the power delivered by a source of alternating current, it's going to look like this. The power is a function of time. It's going to look something like this. Because, these are positive values. Sine squared can be 0, but it can never be negative because we're squaring it. So if we want to talk about average power, we can just take a straight average without doing this RMS thing, because we have all positive values to begin with. So the average power, now again, in general, finding the average value of a function requires calculus, but in this case, we're just going to be taking the average of sine squared, and again, we're going to get 1/2. So the average value of sine squared is 1/2. Now, something nice we can do here, the average power, I'm going to write it like this. Average power, we can write 1/2, or this 2 in the denominator, we can write it like this. We can write it as the square root of 2 times the square root of 2. If you multiply these, you get 2. And so what we find is that the average power, so like over here for a direct current, we have P is IV. Here we have P is I RMS. The average power is the average current, the RMS average current, times the RMS average voltage. So just like P equals IV, except now we're talking about averages. Okay, so again, this is just the basics of alternating current. We don't really yet know why we actually use this. Like why, if you plug something into your outlet, is it in the form of alternating current? We're going to have to talk about inductance before we get to that. But one reason is because of how it's produced. Naturally produced that way. But if most devices use direct current, why don't we just convert it to direct current before going into your house? There's something very essential about alternating current that does not exist with direct current. But that'll be actually 2 lectures from now. So next we're going to talk about something called inductance, and then we're going to look at a special example of inductance called a transformer. And then we'll understand why alternating current is so useful. But this was just covering the basics of alternating currents. So I think I'll stop here.